At depths greater than 1,000 meters, the circulation of the oceans is no longer primarily wind-driven, but is driven by thermohaline effects. In other words, it is driven by the influence of both water temperature and salinity, which results in density differences. The formation of bottom and deep water in the Labrador and Weddell Seas leads to currents below the wind-driven circulation. In addition, at intermediate depths, Mediterranean water flowing into the Atlantic and Red Sea water and Persian Sea water flowing into the Indian Ocean contribute to intermediate water masses and hence to the thermohaline circulation. Stommel put together the first conceptual model of the thermohaline circulation, in which the sinking of dense cold water in the Norwegian Sea and Weddell Sea drives the global ocean circulation, often referred to as the global ocean conveyor belt. Since then, many theories have been developed to explain a deep ocean circulation. The global ocean circulation is of great importance for understanding the Earth's climate and climate change. The flow of water masses can be traced by observing the distribution of salinity and temperature over the ocean's depths. If we take a transect over the Atlantic Ocean, we can see the formation of deep and intermediate waters. The deepest water masses are the Atlantic bottom water, which are formed in the Weddell Sea, and the North Atlantic deep water, which are formed in the Labrador, Greenland, Iceland and Norwegian seas. This sketch shows a distribution in the Atlantic Ocean, where we can see the intermediate water, such as the Antarctic intermediate water. You can also spot the Mediterranean outflow in the salinity plot. The global circulation is driven by these thermohaline effects. Much research is currently being carried out to understand the global ocean circulation and climate change. The weakening of, or even a complete collapse of the thermohaline circulation would have serious consequences. With indications that the Earth is currently in a phase of warming, warmer waters might be transported towards the Arctic and Antarctic, resulting in increased ice melt. The release of the fresh water trapped in the glaciers may result in a reduction in the formation of the deep bottom waters and the subsequent shutdown of the thermohaline circulation. Such changes may have significant impacts on the Earth's climate. The coastal zone represents the interface between the land and water. Consequently, rising sea levels, changes storm tracks, changing rainfall patterns, and river discharges will all impact our coasts. For example, if we look at the Dutch coast, a highly populated region of the planet, we see that as fresh water flows out from the Rhine River, it forms the Rhone-Riffie, an important coastal highway of fresher water that transports material from the Rhine, such as suspended material, pollutants, and biomass. Any change in the river discharge, wind patterns, and storm intensity will impact the evolution of our coasts. Over 40% of the world's population lives in the coastal regions. And the world's population expected to grow to about 8 billion by 2040, the consequences of climate change will be acutely felt at the coasts.